Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In past videos, we've looked at the notion of additive functions, which include things like the dimension of a module or the Hilbert series of a module. And we've seen that these are very, very important invariants for studying module theory. And in this video, I want to introduce the Grothendieck group, which essentially gives us the mother of all these additive functions. So any additive function, the information you get from that, you can get from the Grothendieck group. Okay, so let's make more precise the setting in which we're working in. So I failed to do this in previous videos, but I need to do that now, okay? And the notion that I want to introduce is the notion of a category with exact sequences. So our starting point will be this script A, which is a category like the category of modules over some ring, but it can be more generally some abelian category. So examples of abelian categories include things like graded modules over a graded ring, or things like the category of quasi-coherent sheaves on some scheme. Okay, so that's where we start, and we'll look at four subcategories of that. So just not all of the objects, but some of the objects, but we keep all the morphisms between those objects. Okay, so consider some subcategory C of that. We're going to say it's a category with exact sequences if whenever you have an exact sequence like this inside your big ambient category A, such that the m prime and the m double prime, the sub-object and quotient object, lie inside your C, your subcategory, then the middle one, the extension, also lies in C. Okay, so m prime and double prime in C implies that m is inside C. Okay, so that's the most important condition. The other condition is a slight technical condition, and that is that it has to have a small skeleton. Okay, so this set of isomorphism classes of objects should be a set. Okay, so we're going to work in that setting, and we're going to consider this script C is going to be such a category with exact sequences. And the type of examples that we'll keep in mind, we've looked at them kind of in before. For example, the subcategory of just Noetherian R modules rather than the category of all of these R modules. So let's define now this Grothendieck group, which is going to give us all our additive functions. Okay, so what's the Grothendieck group of this C, this category with exact sequences C? It's denoted K0C. And it's defined as follows. Okay, it's a group. It's in fact an abelian group. Okay, so it's going to be an abelian group, and I'm going to define it using generators and relations. Okay, so what generates this abelian group? Well, for each object M inside my category C, I can look at its isomorphism class. Okay, so these isomorphism classes, they form a set by this technical assumption here. That's going to be our set of generators. And we're going to put some relations on that. And what's the set of relations? Okay, they depend on all the exact sequences that you have. So consider any exact sequence like this inside our category C. Whenever you have this, then we're going to put a relation on these generators. This one here, the extension M, is going to be equal to the sum of m prime and m double prime. So in particular, if m is the direct sum of m prime and m double prime, then inside this Grothendieck group K0C, the class of m is equal to the class of m prime plus the class of m double prime. Okay, that's the complete definition for the Grothendieck group. So let's see a simple example so that you can see what happens. Okay, so we're going to consider C as the special case where R is now a ring, a field rather, K. So we're just looking at finite dimensional vector spaces. Okay, if you have finite dimensional vector spaces, what can you say? Okay, so what can you say about any finite dimensional vector space? Well, it's completely determined by its dimension. And if its dimension is n, then it's isomorphic to k to the n. So the generators are just k to the n, where n is any natural number. Okay, so that's great. And what type of exact sequence do we have? Any exact sequences, we might as well make it of objects of the form k to the n. Basically, any such exact sequence is split. And basically, the only types of exact sequence you have are ones of the form k to the m plus n is the direct sum of k to the m and k to the n. So this is the only relationship that you have, or relation between these generators that you have. K to the m plus n is equal to, the class of this is the same as the class of k to the m plus k to the n. Okay, so when you see this, of course, straight away you can see that if you put n equals 1, there's just one generator for this. You can always write k to the n, the class of k to the n, is just n times the class of k. Okay, and there are no further relations, so basically this K0C, this Grothendieck group, of this category of finite dimensional vector spaces is just a free abelian group generated by the isomorphism class of a one-dimensional vector space. And that's it. So essentially the information that it encodes here is just the dimension of a vector space. But since it's a group, it's got to have negatives as well, so it includes also negative numbers. Okay, so let's try to see how actually this type of idea actually generalizes. Okay, so we're going to see now how the Grothendieck group really is a universal sort of, gives the universal additive function. So all additive functions can only give you information really about this Grothendieck group. Okay, so the first thing is, well, given a Grothendieck group, how do you get an additive function? Well, we get one as follows. So suppose we have some object of C, M. We're going to define chi of M to be what? So you can look at the isomorphism class of M and then its image inside this Grothendieck group. Okay, so by the very definition of how it's set up, right, this is an additive function, right? So whenever you have an exact sequence like this, you have the correct equation. So it is an additive function. And that's basically the reason why we defined it this way. Okay, we defined it so that tautologically we get an additive function. But what's really interesting is that this additive function chi is actually the mother of all additive functions. Okay, so what does that mean? Suppose you're given any additive function lambda on this category with exact sequences C. Okay, so its values will be in some abelian group. Let's call that abelian group A. Okay, well, I claim that you can actually get it from this one here, this chi here. So how's that? So basically what happens is that if you there exists a unique group homomorphism from this K0 of C to A. And how is it defined? Okay, so what special property does it satisfy? It satisfies this special property here. Okay, so basically if you do chi of M, that's inside now this K0 of C, if you apply this phi to it, then you'll get an additive function from this category C to A, and that's exactly the lambda that you have here. Okay, so it's very, very easy to actually define what this function is. Okay, so you look at the generators to define this function on this, so you just have to check the generators, define it on the generators, and then check the relations hold. Okay, so define it on the generators are you pick any object M inside the C, and how do you find chi of M? Phi of that chi of M. Okay, so phi of that M here. So basically you define it as lambda of M. Okay, and then you have to check the relations hold. But that holds precisely because lambda is an additive function. So really it's defined tautologically so that any additive function lambda can be gotten from this chi here by this procedure here. Now the Grothendieck group may seem like a rather abstract and strange object, but there's actually a good chance that you've seen incarnations of it before. So I want to show two examples of such things you might have seen before. So the first one is the connection of this Grothendieck group with the class group that you see in algebraic number theory. Okay, so let's start with R is some ring of integers in some number field K. Okay, so by ring of integers I mean something like Z or some integrally closed finite extension of Z inside inside a number field. Okay, so it might be Z, the Gaussian integer Zi, or something like Z adjoin the square root of -5. Okay, C as usual would just be our category with exact sequences of finitely generated R modules. And the first thing that I want to do is to give an additive function so that we can get a bit of a grip of K0 of this C. Okay, so the first one is called the rank function. Okay, if you're given any finitely generated R module here over such an R, this R is actually a domain, its field of fractions is K, so what we can do is we can tensor up by K, so K tensor Rm, that's a vector space over K, it's finite dimensional because M is finitely generated, so you can say what's the dimension of that. And it's quite easy to see that this is actually an additive function. Okay, since you have an additive function like this, that gives you straight away, by this universal property that I mentioned for Grothendieck groups, a rank function from this group, this Grothendieck group K0C, to where the values of this sit. So the values here sit inside Z, they're just dimensions. Okay, so this rank function, another way to think about it is that, remember in this case here, these are Dedekind domains, so you can talk about a structure theory for finitely generated modules over this M. Okay, there'll be some which will be finite modules. Okay, there's a torsion bit and there's a torsion free bit. Okay, so you can look at the rank of that torsion free bit. So if it happens actually to be a principal ideal domain, that just means that torsion free bit will be free, and it's just the number of copies of the ring R. Okay. Okay, so that's a proposition that we'll need to understand what's going on. Now, of course, the ring R itself has rank 1. So 1 is in the image, so this is actually a surjective map. Okay, so to understand what this K0C is, okay, you've got a map from here to here. Okay, and I guess the most important thing is to understand the kernel. And the kernel, I'm going to try to understand using something called Steinhaus's theorem, which I won't prove, but it's a very, very important result in algebraic number theory. Suppose you have two ideals I and j inside this R, okay? You might want to take direct sum I, direct sum j. What's rather interesting about this, well, firstly, these each have rank 1, okay, because they're non-zero inside this R. So this is rank 2. Well, it's isomorphic to a rank 2 module in a very different way. It's R direct sum Ij. Ij is the product of these two ideals inside R. Okay, I won't give a proof of this, but this is a very interesting and important result. And it's actually going to tell us about this Grothendieck group. Okay, so suppose you look at this rank function that I mentioned up here from this Grothendieck group K0C to Z. Okay, we saw it's surjective. Then what's its kernel? I claim its kernel is actually just isomorphic to the class group of R. Okay, so this is a very, very important object inside in number theory. So basically, it's given by isomorphism classes of ideals. And the way you get the group structure on this, what's it called a class group, it's actually an abelian group, is you just multiply two ideals together inside the field of fractions or inside R itself. Okay, so that's the multiplication that you get. Okay, so let's see what this isomorphism is. Okay, I claim there's an isomorphism of the class group of R with this kernel of this rank. Okay, so I'm going to start with some isomorphism class of an ideal here. There's I. Okay, so we take that, and I want to send it to something that's rank 0, okay, in the kernel of the rank. So it's rank 0. Okay, now this is rank 1. Okay, so basically to get something that's rank 0, I better subtract it from it something that's rank 1. Okay, so there's a canonical thing, and R has rank 1. So we can look at the inside the Grothendieck group, right, the difference between R and I. Okay, so of course, just by the definition of the Grothendieck group, the relations inside here, this is just the image of this module R mod I inside the Grothendieck group. Okay, that's all it is. So you go passing from here the I to the corresponding quotient. Okay, but that's inside the Grothendieck group. Okay, so I won't prove this, but this is a very nice result, which tells you that actually this Grothendieck group, what does it look like? Okay, so firstly, it's an extension. It contains more information than just the class group. Okay, it has some large subgroup, which is the class group, or it might be a small subgroup. It could be 0. Okay, it has a subgroup, which is the class group, which is a very, very important invariant in number theory. And the rest of it, so when you quotient out by this class group, it's just gives you the rank of a module, which is very, very important invariant of a module. Okay, so that's given by the fact that it maps to this Z surjectively. Okay, so what I want to do is to see, well, where does this homomorphism come about, and why is it a homomorphism? And the key reason why is Steinhaus's theorem. So let me just show you that. That's all I want to say about how these work out. Okay, so let's see. So what do we have to do? We have to show that phi. So this map here, when we apply it to a product inside this class group, or so that's I times j is the class of ij. You get what? You get phi of I plus phi of j. Yeah, okay, that's what we want to do. So what's phi of ij? By definition, you just look at the class of R minus the class of ij. And now this is where Steinhaus's theorem comes into play here. So basically, Steinhaus's theorem is going to convert a product of these ideals to direct sums and differences, so to speak. Okay. So basically, Ij is essentially inside the Grothendieck just I plus j minus R. So when you subtract this Ij, you have to add R and subtract I and j. So when you subtract Ij, you're going to add R to get you 2R and subtract I and j. And now what's this? So you can break this up as 1R minus I plus the other R minus j. R minus I here is the phi of I, and the R minus j here is this phi of j. And that shows you that this phi is actually a group homomorphism. And it's actually the group homomorphism which is going to give us this isomorphism. Okay, so this is a really nice result, which really tells you that you might have seen this Grothendieck group essentially in this guise before. It's essentially just the class group extended by, well, you want to study not just ideals or things of rank 0, but things of general rank as well. And basically the only thing you can do is just add more copies of R. Okay, so let's look at another example where you might have seen the Grothendieck ring before, and that's in the theory of group representations. Okay, so I want to show you the connection with character ring. So we start with G here as a finite group, and to simplify the treatment, let's work over the complex numbers, C here. And as usual, the category with exact sequences we want to look at are just finitely generated R modules, Noetherian R modules. Okay, so let me just remind you some theory of group representations. Okay, so firstly, the isomorphism classes of these R modules. If it's a finite dimensional R module, you can break it up into a direct sum of irreducibles, and there's a finite number of them, let's say D of them. Okay, so V1 up to Vd, they're going to be the irreducible modules. Okay, and remember, these irreducible modules correspond to representation, so each of the group elements act on these finite dimensional vector spaces, and since each of the group elements act to each of these group elements and each of these irreducible modules, you can talk about the trace of that action, of the endomorphism. Okay, so they'll give you the characters chi1 up to chi d. Okay, so the facts that we need to know is firstly, any finitely generated R module V is just a direct sum of some of these. Okay, that's the first point. The second point is that one very nice thing that you have for studying these R modules, which makes it really, really easy, is character theory, which is a form of Fourier analysis, really. Okay, so what happens here? Okay, so if you're given a V inside this R mod here, you can associate to it this character, right, which is a function from G to C, as I mentioned before. For every group element inside here, G, okay, it's going to act on this V, okay, it's an endomorphism of V, so you can talk about its trace, and that's the corresponding value that it has there. Okay, so these are functions, and you also have this function which assigns to this R module V this function here, and this is inside some abelian group. Okay, this is this abelian group A equals just the functions from G to C. Okay, so basically this is just the order of G elements, okay, that number of copies of C. Okay, that's what this is, and you can just add, well, this is even a vector space over C, let alone a abelian group. Okay, okay, and it is an additive function. If you have a direct sum of modules here, okay, then chi of the direct sum is where you just take the sum of those two functions pointwise. Okay, that's all you need to do. Okay, so we have an additive function. So once you have an additive function, we can compare the Grothendieck group, chi 0 of C, with that abelian group CG. Okay, so, and what's the image of that? Okay, the image of that, well, remember the fact that every V is a direct sum of these VIs. It's a character theory, and if you analyze also the example of the Grothendieck group of the finite dimensional vector spaces over a field K, that example there, we'll see that basically this Grothendieck group K0 of C is isomorphic to the Z linear span of these characters, irreducible characters chi1 to chi d. Okay, so that's often denoted R of G. Okay, it's like a character ring. Okay, so just the Z linear span of chi1 up to chi d. Okay, so before, when this was a finite dimensional, the category of finite dimensional vector spaces over a field, the only thing you could get was direct sums of the field with itself. Okay, so k to the n. Okay, they're the only isomorphism classes, so it's generated by just one copy of that k. But now, instead of just direct sums of a single k, you can have direct sums of v1s with v2s and so forth up to vds. And so now you have several copies of z, so it's chi1 up to chi d. And these are linearly independent, so really you're just looking at the z linear span of these characters here. Okay, but what's really nice in this example, so of course here you can see this abelian group is just a free abelian group with D generators. What's really, really nice is actually you've got more structure on these two gadgets here. They're not just abelian groups, they even have a multiplication. Okay, so let me go through how that works. Okay, so the example here is quite easy. Okay, so here these are functions from G to C. Okay, so C is some ring, so you can multiply in the ring. So you have pointwise multiplication inside here. Okay, and you can see actually this is closed under multiplication, pointwise multiplication. But what about inside the Grothendieck group? Okay, suppose you have the class of V times the class of W. Okay, so V and W essentially just are R modules. Okay, so just representations of G over the complex numbers. Okay. Well, the thing is that you can take the tensor product of these two representations over C, and this is also a G module, a complex representation of G. Okay, so you can look at the class of that, and basically it's quite easy to see that you'll get a ring structure on this. So, for example, associativity here follows from the fact that the tensor product is associative. Okay, so that gives you that straight away, and you can show that there's also a 1 and so forth. Okay, so this is indeed a ring. And this isomorphism that you have is actually an isomorphism of rings. Okay, so really you use this ring a lot to study representation theory. And so another way of thinking about it is that this ring is basically just the Grothendieck group of the C, but now this also has a ring structure, so it's the Grothendieck ring in this case. Okay, and the reason why that's true is very simple. Okay, if you want to take the character of this, how do you get that? You just multiply the character of V with the character of W. So this also gives a very, very important example of the Grothendieck group that appears in mathematics. I hope you enjoyed this adventure in pure mathematics.